Yeah, I guess I'll date myself, but in getting ready for this, I looked back and I think the first talk I gave at Coast was in 1984. So a few of you probably weren't born then. John Dunham might have been there, but maybe not too many others. But anyway, as Eric mentioned, I'm going to talk about the turbidites in Ventura and also the techniques we use to characterize them, integrating lots of different types and different scales of data, and then with the ultimate goal of eventually building geologic models. So there it goes. So one of the general themes we're going to push today is that stratigraphy and sedimentology are actually critical elements for characterizing reservoirs. And that's because they let us predict things away from the wellbore. I think many of us have seen, quote, geologic models where people take two surfaces, take a data from a couple wells, apply some geostatistics and call that a model. That may be useful for some purposes, but I think what we'll show you is the techniques here give you a much better, more robust model that you can use for prediction and characterization. So two of the key elements are we have to identify the key stratigraphic surfaces and then also characterize the rocks and the rock properties between those surfaces. So we'll look at the techniques for integrating the data from many sources at many scales. And then we'll also look at the deep water depositional systems for Ventura Field. So first, a few fun facts about Ventura. Many of you know some of these. Produced for over 100 years. It's a 9-mile long field, thrust faulted, very thick oil column, had peak production over 75,000 barrels back in the mid-50s. It produced 1 billion barrels as of 2009. I don't know what the total is now. And water floods were initiated many decades ago, and it's still producing about 10,000 barrels a day. So the photo shows the air photo with the coastline. You see 101, the Ventura River, Highway 33 bisects the field. And then here's Poinsettia Pavilion where we normally are, and hopefully we'll be back there in a few months. So this field was very important for the economic development of Ventura, but it also has significant historical value in terms of understanding deep water deposition. And that's because back in the 30s and 40s, most geologists thought that coarse clastic sediments were really the realm of non-marine and shallow marine environments. But a micropaleontologist and basically a process experimental sedimentologist got together, and they proved pretty convincingly that the thick sands in Ventura with the interbedded mudstones with deep water foraminifera in them had to be deposited in deep water, and therefore gave these turbidity hypotheses a lot more ammunition. I think convinced a lot of people that these were valid mechanisms for depositing thick sands in deep water. And then in the late 70s and early 80s, Ken Shu, who was with Shell at the time, he published a bunch of important papers about turbidites using Ventura as his framework. He talked about geometry, he talked about facies, he talked about rock properties, and these really, I think, set the stage for a lot of future studies. And he also identified some of these elongate lobes in the basin, which I think were, kind of a first here. Then there wasn't very much published for the next few decades, and then in the time frame of about 2007 onwards, when I joined with ERA and got together with a group of people, we looked at the field again. That work went on for about 7 years. And so I've listed some of the people, I'm sure I'm missing some, but I've listed some of the people that were involved in different aspects of the project. So it had ERA folks, it had Shell folks, it had some people from Stanford, and a few others that chimed in with some different expertise at various times. In terms of the field itself, it sits, this is a really simplistic diagram, but the field sits in the center of this elongate trough. And this trough basin is essentially maintained by active tectonics, the San Cayetano fault system to the north, the Oak Ridge and related faults to the south. And basically what it did is it kept the Ventura Field location in the center of this depositional trough for quite some time. And so the predominant sediment source was actually to the east, and we had a lot of east-west transport through this basin. So just to set the stage there. And then this is the photo just about everyone sees when they talk about Ventura Field, but it's actually not Ventura Field. As many of you know, it's actually the San Miguelito Amphitheater. It's next door to the Ventura Field, but it does show a few key elements. One is this really thick package of sediments, clastic sediments at the surface, and then it also shows the structural style that we see in the subsurface. So we won't talk about the structure in this particular discussion, but I just threw one slide up that some of the shell geologists had put together back in the 50s, 60s, and 70s. And what you see on the left is one of the cross sections that they did. These really thin black lines, these are all wells. So they had tons of well control. And then they basically have highlighted a couple of, in orange and yellow, a couple of the horizons and the faults. And they built these one-to-one cross sections at 500 and 1,000 foot spacings throughout the field area. And they used this to plan and drill their wells. And it's amazing how accurate they were. And then you also see the green shading on this cross section. It shows just how thick this oil column is. And it also shows you that the faults in the stratigraphy help control the distribution of oil. So it wasn't a simple field to develop. They had a lot of complex problems they had to solve to decide how to best produce the field. And then to the right, you see kind of a standard stratigraphic column, but this just shows, for those of you familiar with well logs, this kind of serrated SP here shows the sand mudstone package that persists for over 10,000 feet in the field. This is a perspective view, again, from the south. You see, again, the coastline here, Highway 101, the Ventura River coming out, bisecting the field. And then you see underneath here, the 2,500 plus well bores that were used to define and develop the field. So quite an incredible database. The other thing that's important here, though, is we have this, we see some of the 3D representations of some of the reservoirs. And these heavier lines that you see, these are 1,000 foot increments. So on this one particular reservoir surface, we have over a mile of relief. And that becomes really important when we start studying the field, because what that does is it allows us to look at some of the rocks that are in the outcrop and basically use them as analogs because they're in similar depositional settings to the rocks in the field. So some of you that might be sedimentologists might already be interpreting this. The first thing you'll probably do is look for, stratigraphic bounding surfaces. Then you might start looking at the fabric and the internal geometry. Maybe there's some fining upward beds there, maybe some planar parallel beds, and then maybe some cross beds. So many of you would recognize this as a partial Bauma sequence. And this is the point of going to the outcrops, is we can see these types of structures and many other structures that are very similar to what we see in the subsurface. So this is an example, in case some of you aren't familiar with looking at cores. These are slabbed core photographs. So these are cores sliced in half, basically, with they're 4 inches in diameter, and then they're photographed in both plain light on the left and ultraviolet light on the right, and that highlights hydrocarbon, can highlight hydrocarbon saturation in the rock. And then if you're not familiar with looking at cores, these circles, these are core plug samples, core plug locations. And that's where samples are taken to measure things like porosity, permeability, mineralogy thin section. So anyway, we see over here very similar sedimentary structures to what we saw in the outcrop, Bama type bedding, but we also see these long, thick intervals of basically homogeneous, sometimes graded, sometimes not graded sandstones. And these are also common throughout the field. In fact, we see a really wide variety. We don't just see typical Bauma sequence turbidites here. Some of the coarsest grained units we see on the left, we see angular mudstone rip-up class with pebbles in a sandy matrix. We can see pebbles, granules, and coarse sand in a poorly sorted matrix here. Or again, more coarse sand and pebbles, but also fluid escape structures here. So these coarsest grain units typically are interpreted as areas of some local erosion, but also very rapid deposition. Similarly, we see what have been termed amalgamated sandstones. So these aren't quite as coarse for the most part. They're generally granules to medium sand, but they've been termed high density turbidites. And what you notice here is that there's not a lot of breaks in the bedding. In fact, the breaks that you see are typically grain size changes, like here where we go from a coarse to medium sand into a pebble, coarse to medium sand into a pebble. So that's what often defines these flow units. Sometimes we have caps of finer sands near the top, but the key element is there's really no mudstone between any of these depositional units, hence the name or the term amalgamated sands. And then we also do have intervals with lots of thin-bedded turbidites and mudstones, and these are more of the classic or the low-density turbidites. Interbeds of fine, medium sand and mudstone, planar parallel, laminations and current ripples. And these are where some of the Bauma type flows or Bauma type structures dominate. So I think for the most part, we can be pretty comfortable putting this within a very simple depositional model, right? Where we have these coarser grained units, typically most proximal near the kind of the source of the sediments. Maybe as we get further down the system, we'll see more of these amalgamated sands without a lot of mudstone interbeds. And then as we get further down into the system, we run into these thin-bedded sandstones and mudstones. And it turns out these are really important distinctions in terms of what the reservoir quality is of these sands, of these reservoir rocks. These amalgamated sands, what we're going to call high density turbidites, we'll talk about in a minute. But again, fewer mudstone interbeds, essentially structureless to graded, thick beds, poorly sorted. Turns out they're going to have lower porosity, but in terms of reservoir, they're going to have higher net to gross and a higher vertical perm relative to their horizontal perm. And that's in contrast to the non-amalgamated lower density turbidites, which we have common mudstone interbeds and caps. We see more of the Bauma sequence type bedding, thinner beds. These are going to turn out to be better sorted, higher porosity, but essentially have lower net to gross and obviously lower vertical permeability because they have to get through these mudstones. So it turns out that the depositional processes really impact the rock properties of these units. The high density turbidites, which are generally the coarser grains, pebbles through medium sand, they're going to be deposited from these higher energy, high sediment concentration flows. And the big distinction here is that in these flows, the grains are supported not just by fluid turbulence, but also by grain to grain interaction. That contrasts with the low density turbidites, again, smaller or finer grain sizes. But again, the big distinction is these particles are supported only by fluid turbulence in the flow, and therefore they become better sorted and actually have better reservoir properties in terms of porosity and permeability. So we can look at the statistics for some of this. What you see plotted here is porosity on the y-axis going from 0 to 20%, and then increasing grain size on the x-axis. And so we'll ignore the mudstones for now, but the fine and medium grain sandstones are here in the pink. And then as we move to so these are going to be the generally thin-bedded turbidites. And then as we move to the coarser sands, the generally amalgamated sands, you see a big drop off in porosity, right? The range here goes from, for this medium sand, goes from about 25 on down to about 15, whereas the range for the coarse sand goes from maybe 20 or so on down to 10 or less. So we're going to turn these two distributions on their side just to show this in a little more detail. So here, the medium sands have a modal value of 20% porosity, and the coarse sands are actually, much lower, around 16. So by understanding the different distributions of some of these rock properties, we'll then be able to utilize that in our geologic models. Okay, we also see similar phenomenon in terms of how the beds stack. So this is a core photo with porosity values overlain in the blue scales, in the blue squares scaled 0 to 30. And then on the right, you see essentially a histogram of grain size from detailed core description. So the yellow line here denotes the medium grain size. So what you see here is relatively constant porosity here at the base. This whiter unit's actually a cemented sand, but those represent the amalgamated, thicker bedded pebbles to coarse sand. And then once we get above here, you can start seeing these fining upward package that represent more the Bama type sequences. And for each one of them, we have higher porosity values near the tops of the structure. So we're seeing the impact of the stratigraphic stacking in terms of the rock distribution. We can see a similar thing on a much larger scale. Here we have 120 feet of core data represented. I know you can't see any of the detail of the core photos, but the red boxes, again, are porosity, again, from 0 to 30. And then these grain size histograms here come from the core description. So they show you the coarser units near the base, and we're getting more finer grained and more thinly interbedded as we move up. There's also a color scale here that ties back to this color stack to basically show you the same thing. So we have a fining upwards stacking pattern overall over this about 100-foot interval. We have this coarse base here, abrupt change in stacking. And then as we move up, we again get into these finer grained units. So overall fining upward stack. And then if you look at the porosity, overall, we're basically getting better and better porosity moving up with these finer grained units. So this is the kind of information we can put into our geologic model and try to get a better representation of the fluid flow characteristics in the subsurface. We see a different type of stacking. This is a different well. It's tied to an image log in this case, which we won't talk about too much today, but there's the core photos, again, about 120 feet of core. And what you see here is we have almost all amalgamated beds, coarser beds here. We have one small interval of thin-bedded turbidites here. So if you notice, well, first of all, this is almost constant porosity through the thicker bedded amalgamated beds, and it's lower in some of the values we see here in the thin bedded units. And so one of the techniques we can use to try to quantify that is to look at mercury injection capillary pressure data. And in this case, it's a histogram. We can represent that data in terms of pore throat diameter. And so when we do that, we can look at one of the thin interbedded units down here. You see we have a peak here at about 100 micron pore throat diameter. And that compares to the coarser bedded unit, or the coarser bedded unit, which is actually about 10 microns. And if you look at the thin sections, you can clearly see how much better sorted the lower one is than the upper one. Now, it turns out the porosity of the lower one is about 20. The porosity of the upper one is about 15. So about 5 porosity units different. But the big difference comes in the permeability, where the air permeability in the lower one is essentially an order of magnitude greater than in the upper coarser grained unit. So in terms of flow characteristics, those can be important. And then I said we weren't going to talk too much about borehole images, and we won't have time for that. But I just wanted to show you one example of some of the data that we can gather from these. And we actually did use these in terms of trying to understand our depositional systems. You know, most people use these borehole images, which are essentially an electrical image of the borehole unwrapped. They use them to identify bedding surfaces, maybe calculate structure, orientation. But there's a lot more you can get from that. And one of the things we can see pretty clearly in some of these good images is the rock fabric in the facies information. So in this particular interval, we have some thin bedded sands and mudstones. And then we have this turbidite type unit here, where we actually have clay rip-up class at the base. And then the way the image log works is the brighter colors are essentially sandier here, and the increase in the darker colors are muddier. We can actually see this kind of fining upward package going up here. And the other thing we can do with this is we can compare the image log to a standard well log. So in this case, there's a gamma ray plotted over the top. And I think what you see is that if I look just at this lower part, if I had a gamma ray and I was trying to, let's say, calculate a net to gross, I might draw a line across here. And I'd say, oh, yeah, this is sand and this is mud down here. But it turns out that even within this mudstone unit, it looks like I've got, you know, a fair bit of interbedded sand. So there's a number of things we can get from image logs, both depositional information and also quantifying reservoir parameters that we've used in our work. But the big piece that we're going to talk about here is how we calibrate the well logs to the core. So here, we're going to define what we call petrofacies, which are basically facies defined from the petrophysical data. The technique we use is called a self-organizing map, which I'll explain a little bit in a minute. It basically requires still that we align the cores. So this is core description over here, core description of about 100 and about 200 feet of core. We have to align the core then with the well log segment we're going to use, in this case, gamma ray, neutron, and density. And then what we do, it's a little bit different than some of the other techniques people have used. We don't tell the program what facies we're looking for. Instead, we let the logs basically self-organize into clusters or groups. And then we can look at statistics and see where we're most confident of those groupings. And it turns out for these data, you can see the color code, we broke out the groups at the end, but we were able to define 6 distinct well log populations using this technique. And then the next big step is to relate these petrofacies classes back to the core description. So that's basically going back and saying, okay, I'm in petrofacies class 1. What do I have in the core here? I'm in petrofacies class 2. What do I have in the core here? So when we do that, here's what we came up with. Petrofacies 1 was 70% mudstone and mostly fine sands. Petrofacies 2, obviously 48% mudstone, less mudstone in petrofacies 3, picking up more and some coarser sands. And then petrofacies 4 is almost all medium and fine sandstone. And when we get to petrofacies 5 and 6, we're getting into predominantly the coarser units. So we really, what these petrofacies tell us is a probability that we have a specific facies at a certain level. It's not really telling us what that facies is, but it's a probability. So this color scheme you'll see throughout much of the rest of the talk. And so basically the reds are the coarser units, the yellows are the finer grained sands, and the grays or greens will be the mudstones. So we can circle back then and just make sure that we're getting data that's similar to our core data. And this is basically taking the porosity distribution from the petrofacies. And so I think here you can see the medium fine sands are in the blue, and those actually have the best porosity. The coarser sands and the very coarse sands and pebbles, they basically have lower porosity in the same ranges that we saw with the core data. So this gave us confidence in that we could use this classification to also distribute our reservoir properties. Okay, that helps us out at the wells, but now what do? This is actually petrofacies of over about 500 feet of well data from 4 different wells separated by about 5 miles. So, you know, our task is going to be, okay, great. We know what happens at this well, or at least we have a pretty good idea what happens at each well, but how do we get from one well to the next? And that's where we go back to the outcrop, and we can use some of the observations that we gather from the outcrop as well as from the well logs to help us understand our correlation framework. So this again is from San Miguelito Field, but it's one of the few places where we can see hundreds of feet of stratigraphy. And I think you can see even in the mist here that these are relatively planar parallel beds, sheet-like geometry. But if we zoom in pretty closely, we can start to see there's some thickness changes in some of these sand packages as we move laterally. So the vertical stacking seems pretty consistent, but we're seeing some subtle lithofacies changes over hundreds of feet. We also can look in outcrop, we have some good exposures of these thicker amalgamated beds. And you can see one here. We have a nice stack of fine-grained mudstone and thin sands, and then it's pretty abruptly overlain by this coarse grain unit. There's some loading and actually some flute-type casts on this, so we can get an orientation of transport. But one thing you'll notice is even though it's erosional at the base and there are some mudstone clasts here, it's not really scouring down. It's a gentle scour. It's not like a submarine canyon where we're cutting steeply into the strata below. So these are mostly low relief surfaces, sometimes with loading and flow features on them. And even within amalgamated units, we see other surfaces, but they're similar, right? There's not a whole lot of scour and truncation on this. It's relatively low angle. When we start looking at some of the thinner bedded units, we see, again, some lateral variation, some scour, but it's low angle. It's not like we're carving out 40, 50 feet of strata below. And then even when we look at some of the really thin bedded sandstones, we can start to see some of them are actually terminating. We can find these pinching out. So we can use these observations and other observations that we gathered from our well data to come up with some guidelines for correlation. And we listed some of those here. So, you know, some of the best surfaces for well log correlation are going to be either the bases of some of those thick amalgamated sands or some regional flooding abandonment surfaces that we can see on the logs. The scour and truncation that we commonly see, it's relatively shallow, right? It's on the order of tens of feet. It's not hundreds of feet. And so this generally planar geometry lends itself to more of a sheet geometry setting rather than a channelized setting where we're carving out lots of stratigraphy below. These amalgamated sands, they persist over hundreds to thousands of feet, and we can really correlate them pretty well on our typical well spacing. We've seen the thin sands are going to be less continuous, so it's going to be more difficult to correlate those between wells. And then the other thing we've noticed is we've got locally consistent vertical stacking patterns of lithofacies. So what that means is if I have a fining upward sequence in one well, I'm not going to expect necessarily an aggradational sequence in the next. They're usually going to match. So here's an example of applying that to some of the well data that we had. We have a nice flooding surface here, this DC surface, which sits below this really thick regional mudstone. So that's a good constraint to our stratigraphy. We also have another mudstone flooding surface down here, highlighted in the blue. And then between that, we can start looking at our strata. And here we have a coarse-based abrupt sand bed, another one here. And then as we move up here, we see we've actually lost some thickness, but it's only about 25 feet. Again, it's not hundreds of feet. And it's over a distance of about 2,000 plus feet. So this is kind of fitting the geometry that we've gleaned from the outcrop observations too. And then we have another abrupt base here with another coarser grained unit. And then we have, this is from a core description, we have a fining upward package here and another fining upward package there. So that's basically how we took some of the observations from the outcrops as well as the subsurface and applied it to our correlation framework. And I think we can go back to our depositional model here and pretty easily see how we would fit in our petrofacies, right? We've got the coarser grained units here, probably more proximal source, thinner, but still very sandy units here, somewhere out in this middle range, and then more near the fringes, we get the interbedded sands and mudstones. So no surprises there, pretty similar to what we had before. But one complication for all this is that these depositional lobes are going to create topography, right? So we may start out with one lobe here, but it's eventually going to be, form some kind of positive relief on the seafloor. So the next lobe might move laterally north, the next one might move laterally south. Basically, you're going to get a whole mosaic of these things that fill in, and it's going to create a much more complex facies mosaic than just a simple one-dimensional lobe. So we go back to our correlations again and say, gee, this is going to be tough. I can see I'm going to have trouble correlating some of these. What kind of guidelines can I have? How do I do this? Well, it turns out that for this project, we did what a lot of companies do when they have a tough problem. They bring in an intern. So this is where we brought in Elizabeth Steele from UCSB, and we gave her the tools and our insights and had her develop some of her own insights. And basically, she spent the summer working the well data. And not only did she have all these, but you'll see in a minute, she had many more wells in between to trace out and track some of these different units. So this is what she came up with for this particular cross section, obviously with many wells in between. But you see thickening and thinning of the different units. But overall, the gross sediment packages are pretty much the same thickness overall. And we can check her work by taking a look at, oops, supposed to go there. We can check her work by taking a look at some maps, some thickness maps of some of these different sandstone packages. And so the scale you see here, 0 is the red, purple is 200 feet thick. We'll start at this basal unit, which is how these were laid down. So this second sandstone package, you see there's a real thick right here, 200 feet thick. Again, there's the cross section and all the well control she used. And then the unit that succeeds that, you can see that the thin overlies the thick there. And so the package is basically showing us this compensational stacking. And this is what we see throughout the field. If we get the surfaces right and start tracking it, we see compensational stacking for many of the different sand units. So we won't go into the details of the geologic model, but I just thought I'd show you one example of a realization. The slide on the left, this is just from one particular fault block, and it's about 2 miles in length across here, and these are the wells. But on the left, you see what's called the vertical proportion curve, and this is pretty interesting because I think there's 28 wells here, and they're basically all aligned stratigraphically. And then you look at the facies distribution kind of in a histogram form for each level. And this really tells you a lot about the overall stacking patterns over this interval. So here we start out with a pretty sandy unit, but then probably on a lobe, lobe by lobe scale, we start picking up more and more mudstone. We pick up a sandy unit again. Then we have more of a prograding type sequence, if you will, in terms of more and more sand. And then finally, a really abrupt amalgamated sand unit comes in and basically just dominates over the whole system. So you can look at what that looks like on these little cross-section maps here. And it might take a minute to get oriented, but if you look here, this is actually the cross-section, a slice through the model. And this is a dip slope facing you, so coming out at you. So you're looking at one dip slope and then how it intersects with the rest of the model. So this cross-sectional part is going to be thicker here at the base. And as we move to the top, when we get to the top of the model, it's almost gone. So this is an example of amalgamated layered sandstones without any really continuous mudstone. This is another interval with a little bit more mudstone. You can see some of these patches. Then we have this abandonment surface with mostly mudstones and some fine sands. And then amalgamated sandstones give us the best continuity here. So, within this model, then we can take those relationships we found with porosity and permeability. We probably have to scale them up a bit, but apply them to this model and then have a much more refined model in terms of reservoir properties tied into our stratigraphy and our understanding of the depositional system. And it turns out this is actually very similar. Some independent work that John Rosine did at Stanford. He looked at mostly outcrop data here and a little bit of the core data, but he basically proposed this braided lobe complex for the Ventura deposition, or at least for part of it. And he saw things like sheet-like architectural elements like we did. He had a lot of coarse sediments deposited at high accumulation rates, lots of shallow scouring, and then a lack of the levee channel geometry that you might expect in some submarine fan settings. So just thought I'd show this. The reference is in the back if you wanted to look at that, but it's very similar to what we came up with. So to summarize, we tried to show you how we took data from multiple scales to try to enhance both our understanding of the depositional systems and to get predictive capability for reservoir properties. We tried to use the cores and the outcrops to understand depositional facies, how the lithofacies are organized in terms of stacking, as well as their lateral variation. And then we looked at some of the basic sedimentologic processes and how they impacted reservoir properties. We looked at petrofacies, and we basically built that model to help us extrapolate away from our limited chord wells. And then finally, hopefully I've showed you how it's important to understand the key stratigraphic surfaces in order to build the models. So basically, we think this gives us a much more robust geologic model and the predictive capabilities that we're looking for. Okay, and I think the next slide just has some of the references that I talked about. Okay, I think that's it. Do I give it back to you?